Now that you have a good idea of what an operon is and what it does, I want to teach you about two specific examples. First, the lac operon, and then the trip operon. The lac operon is an example of an inducible operon from your book. An inducible operon is when the substrate, in this case a lactose, binds to the repressor protein, and that causes the repressor to leave the DNA, allowing the DNA genes to actually be transcribed and translated. So an inducible operon is essentially turning the gene expression on. So in this case, when lactose is present, it's going to bind to the repressor called the lac repressor protein in big old red here, and it's going to trigger it to release from the DNA, in other words, from the operator. And when it releases from the DNA, it's going to allow the promoter site to be open, which is going to allow RNA polymerase to bind. So in this example right here, the repressor protein is already bound to the DNA. So when RNA polymerase comes over, there is nowhere for it to bind. It can't transcribe or translate. In other words, with the repressor protein bound here, this gene is off. But once lactose is in the system, maybe you drank a glass of milk, or this bacteria did, once lactose is in the picture, this lactose is going to bind to the lac repressor protein, and when it does that, it causes the repressor protein to actually change shape. And when it changes shape, it can no longer bind to the DNA. And when it can't bind to the DNA because of this conformational change, it can't hold on to the operator, and it leaves. So now the promoter is wide open, and RNA polymerase can bind to that repressor, or the promoter, and RNA polymerase will transcribe gene 1, gene 2, gene 3, and gene 4. And we all know from chapter 10 that RNA polymerase transcribing is going to produce a messenger RNA. As we talked about, it's going to be one continuous messenger RNA that can then be translated into a protein, and that protein will be modified or basically cut into 4 separate polypeptides, producing enzyme 1, enzyme 2, enzyme 3, and enzyme 4. And these enzymes, their function is to actually break apart the lactose into the 2 monosaccharides that make it up so that they can be digested. So now you think about this process going on, well, the lactose is getting broken apart. So eventually there's going to be very few lactose molecules, which means they're not going to be able to bond with the repressor protein anymore, which means that this repressor protein is going to be able to bind again with the operator, thus shutting this gene back down again, which will be good because if there's not enough lactose to bind with the repressor protein, there's not enough lactose to worry about breaking down, so we don't want to waste our energy creating these enzymes. And so essentially, lactose causes this operon to turn on. And so when lactose is present, it says, well, I'm present, so you better make some enzymes that digest me, something to break me down into my monosaccharides. And so again, we can see that happening over here. When the lactose in this green dot is present, it causes the repressor protein to actually change shape. So now this new shape of the repressor protein cannot bind to the operator. Therefore, it cannot block RNA polymerase, and the transcription and translation of this lac operon will happen. Our enzymes will be made, and those enzymes will break lactose down into its monosaccharides. And so this shows us that lactose is an allosteric regulator of the proteins, changing its shape. Now the reverse is true as well. There's a different example which deals with a repressible operon, and our example is going to be tryptophan. Now, with a lac operon, we turn the gene on. With the repressible operon, we're essentially turning the gene off, preventing transcription and translation. So in this synthesis pathway, this is the pathway that actually produces the molecule tryptophan. When you have extra tryptophan present, it's going to bind to the TRYP repressor protein, and again, that's going to cause a change in shape. But this time, when the TRP repressor protein and the tryptophan are bound, it's actually going to cause that repressor protein to bind to the DNA. So it causes a change in the opposite direction. And so now it's binding to the DNA, which means it's going to shut down this transcription and translation process. And so here we have RNA polymerase just doing its thing, transcribing, translating. So we're going to get our messenger RNA strand, right? And that messenger RNA strand is going to get translated and produce a polypeptide chain, which is going to get modified into enzyme 1, 2, 3, and 4. And remember that the function of those enzymes are to take or to build or to synthesize a tryptophan molecule. Now, as you're building these molecules, eventually you're going to get a lot of tryptophan. And you're going to say, well, we better shut this thing off. We don't need any more tryptophan. And that's when excess tryptophan will bind to this repressor protein. Now that repressor protein, well, let's look at this as we do it. So here are tryptophan molecules getting created over on the right. And those tryptophan molecules, being in excess, are now going to bind with the repressor protein. That conformational change occurs, and that repressor protein binds with the operator. And now poor old RNA polymerase tries to come in, but it can't bind to the promoter. Therefore, no longer can we transcribe those genes. And if we can't transcribe those genes, well, we can't translate them either, which means we're going to stop producing tryptophan, right? We already had enough, so why keep making it? Now, again, we look ahead and we say, okay, well, eventually all the tryptophan is going to get used up, which means it won't be there to bind with the repressor anymore, which means this repressor protein won't bind with the operator. Therefore, RNA polymerase will once again be able to come in, transcribe and translate, and make more of the tryptophan. And so what happens when tryptophan is present? Ultimately, well, if it's present, you don't need to keep making enzymes to make more tryptophan. There's already enough. And so, if we look at this picture, we see tryptophan coming in. It binds the repressor protein. It causes an allosteric change. And this time, the repressor protein is actually changed to be active. Now it binds in with the operator, and thus it turns off the gene. It can no longer be transcribed or translated. So in summary, our inducible operons are typically functioning in a catabolic pathway. And so catabolic pathways where you break things down, basically digestion, taking more complex polysaccharides, breaking them down into monosaccharides, and therefore it allows you to produce enzymes only when that nutrient is available. There's no reason to have enzymes to break a product down if there's no product to break down. So once that enzyme, or once that product or that nutrient is available, then those enzymes would be produced. And so that avoids making proteins that are just sitting around, wasting enzymes, wasting resources that could be used for other things. The repressible operon is used usually in an anabolic pathway. You might remember your anabolic steroids from earlier in this year, building or synthesizing things, and so making an end product. And so this case gets regulated when that end product, when you have too much of it, it's in excess, and as a result, it shuts down the pathway so that those resources, nutrients, materials, energy can be used for other, maybe more important sources.